Hi, welcome to Chapter 6, Part 1. Chapter 6 is a little bit different. It is to prep us for skills that we are going to be using pretty much through the rest of the semester and year of organic. When Chapter 6 was added to the Klein textbook, it was presented as a chapter you could just sign as a reading. So it's not something that I spend a lot of time lecturing on, though I do want to guide you through a few pieces of it. And it does average out well because Chapter 7 is kind of a large chapter. So these go nicely together. I'm going to go very quickly through the first several sections. There is some review on enthalpy and entropy, Gibbs free energy, just some kinetics and thermodynamics topics, and then hit kinetics. To talk about where some of these, to give you a little bit of that vocabulary again, to talk about where these reaction mechanisms come from. So we're going to be talking a lot about chemical reaction, work with me here, mechanisms. This is going to be an important word. When we talk about a reaction, we're often talking, A plus B reacting to form, C plus D. Reactants forming products. But that doesn't really tell you the whole story, right? We started to get a little bit of that story with our acid-base reaction when we look at HA reacting with our base, and we form a new bond between the base and the proton, and we break the bond between the hydrogen and the rest of the acid, right? This is a chemical reaction mechanism. The mechanism shows you how we get to our products by which bonds are breaking and which bonds are forming. Sometimes this can happen in one step, like in these acid-base reactions we've looked at, and sometimes it's multiple steps. And how do we know? How do we know these reaction mechanisms are this way? Well, it comes from a lot of experimental data and observation, kinetics and thermodynamics studies. And so that's why you get a little bit of a review. And then in the second half of this chapter, we go through reaction mechanism patterns. So we kind of like we did for resonance, we're going to look at some common patterns that you're going to see throughout the rest of your time in organic. Just to review a little bit here, we do occasionally think about the thermodynamics and think about enthalpy, whether a reaction requires heat or gives off heat. Right? Is it endothermic? Is it exothermic? Does it absorb energy? Does it give off energy? Breaking a bond always requires an absorption of energy, but forming bonds always gives off energy. So it's that combination of bonds breaking and forming that determines whether the enthalpy is positive or negative. There are two ways bonds can break. This is important. We have looked only at heterolytic cleavage so far. That's where both electrons in the bond go in one direction, right? So when we look at, say, the bond breaking here, that is a heterolytic cleavage. Both electrons that were holding H and A together go with the A atom, go to that what is going to become your conjugate base. We will observe homolytic cleavage when we get to definitely chapter 10. I think there's an example of a homolytic cleavage even in chapter 9. And that's where the two electrons of a bond go in separate directions. And that is when you're going to wind up using your single barbed arrow as opposed to your double barbed arrow. You've noticed by now that in your homework, you always have that option. And if you pick the wrong one, it will be wrong. I will be asking you to show me mechanisms in lab reports as we move forward, or I might ask you questions about mechanisms in exams. And the type of arrow you choose is critical, right? We are in an analytical field here, right? We're very concerned about attention to detail in chemistry, and that detail is important, right? One communicates movement of a single electron, the other communicates the movement of two electrons, right? So it's kind of like proper grammar for us. We're not going to worry about specific bond association energies. This is something you covered in Gen Chem, and we're not going to be doing the math behind this, but this is, again, just a little bit of a review chapter. Okay, we've discussed, endo and exothermic reactions. Every now and then that will come up when we talk about certain reactions, and we'll review that when we get there. We will see a lot of energy diagrams as we learn about new reactions, and just some things to review, right? Energy is always increasing as you go up. In this case, it's enthalpy, but a lot of time we're just talking about general energy. The reaction coordinate is the x-axis, so if we had, say, A plus B going to C plus D, your reaction coordinate might look like this. So if your starting materials are higher in energy than your products, this is an exothermic reaction. If they are lower than your products, it is endothermic, right? So it is a way to visually represent that change in energy. These energy diagrams used to describe the kinetics and thermodynamics of a chemical reaction. Again, there's Leroy. We're getting close to dinner time in the Jones household. So as I can keep this going, we're going to go ahead and let these boys outside and keep talking about thermodynamics and enthalpy changes. All right. So we will see these types of energy diagrams as we start to talk about more complicated reaction mechanisms. Sometimes you will see very simple reaction mechanisms, right, where we go from starting material, let's say, to product. We're not going to worry too much about their energy. Sometimes it will be a simple up and over with one maxima and then the minimas at the starting material and the products. As we get more complex, we're going to see sometimes more interesting reaction diagrams. So we want to make sure that we understand generally energy is on the y-axis. The reaction coordinate, or what happens as we go from starting materials to products, is on the x-axis. Again, we are skipping through this because you've done this already. We're not going to be calculating delta H in this class. Entropy also plays a role, right? So enthalpy is a kind of a measure of the thermal energy. Entropy is a measure of chaos, right? It's kind of how you learn it in Gen Chem. It can be described as disorder or randomness or freedom. Entropy takes into account the vibrational, rotational, and translational states that is distributed amongst the compound. It has to do with the kinetic energy. It has to do with the number of particles. So, for instance, if we are doing A plus B yields a single product, right, entropy is decreasing. We're going from two materials to one. Whereas if, let's say, we have a decomposition where A goes to B plus C, generally the entropy is increasing there. We are not going to spend much time talking about entropy in this class, and so it is important just as a reference that you know what the word means in case it comes up in discussion, but we aren't going to be calculating it. We're not going to spend a lot of time thinking about entropy or Gibbs free energy. Right? Gibbs free energy takes into account both sides, entropy and enthalpy, and it helps us to determine whether or not a reaction will go forward spontaneously or non-spontaneously, right? Non-spontaneous means that we would have to do something continually to keep that reaction going. Now, of course, on a practical level, that's important when you are setting up a reaction. But what we're going to be focusing on is reactions that we're going to memorize what steps they go through to get from A to B, to get from start to finish. Not necessarily a lot of time on is it spontaneous or not. So again, these are really just reviews when you're looking at these first few sections of Chapter 6. Enthalpy, entropy, and Gibbs free energy are big topics you learned about in Gen Chem. If you're in chemical engineering, you will talk a lot more about thermodynamics. If you're a chemistry major, you will see these topics come up time and again in your various advanced chemistry courses, especially like when you get to physical chemistry. Equilibrium, that's another topic you probably spend a couple chapters on in Gen Chem. That you are going to see quite a bit of reference to throughout your time in organic, especially considering equilibrium arrows. We've already talked a little bit about this with our acid and base discussions. When we look at reaction steps, sometimes you will see the equilibrium arrow, sometimes you will see the forward arrow. This is determined based on the overall equilibrium. If the equilibrium strongly favors the products, and we're talking about usually a very large threshold, you may see only this forward arrow. If you tend to have a fair equilibrium between starting materials and products, you may see the equilibrium arrow. When we get into reaction mechanisms, I don't care as much about these two types of arrows because I am frequently just trying to move in that forward direction to learn how we get from A to B. But knowing what that arrow indicates is important, right? It's a dynamic equilibrium as opposed to just moving forward or a resonance arrow, right? Remember, resonance arrows don't indicate movement. Resonance arrows indicate, what's the right word for this? Indicate a lack of kind of completion in a Lewis structure, right? You need multiple Lewis structures to understand that molecule or that intermediate. We will see resonance arrows as well, and it is very important that we recognize the difference between these that actually show chemical reactions, right? Bonds breaking and forming, and this one, the resonance arrow, that does not show bonds breaking and forming. You notice you still see a reaction coordinate over here. You still have energy of some sort on the y-axis, and then the direction of the reaction on the x-axis. We're not going to spend a lot of time talking about concentrations, but kinetics do come into play in determining reaction mechanisms. So occasionally we will talk about kinetics, and this is where Gibbs free energy is related to equilibrium, and that kind of takes us in from thermodynamics into kinetics. And you can get into experimental studies. We're not going to do the math behind this. What kinetics can help us to determine, though? Let's see. Here we go. Kinetics, relationship to delta G. I want to get to the slide that will make sense for us. Okay, so kinetics, 5 factors that go into studying kinetics. Concentration of reactants, activation energy, temperature, geometry, and steric. So what three-dimensional space is your molecule taking up? Because for A and B to react, they have to collide. They have to collide with enough energy to activate, right, the bonds breaking. So that is related to the temperature, right? Because the average kinetic energy is related to temperature. And A and B have to run into each other in the right orientation to get a reaction. And then sometimes the presence of a catalyst. There will be some reactions where we talk about that. Studying the concentrations of those reactants can help you determine things like first order, second order, third order reactions. Whether or not a reactant affects the rate gives us information about how it is important to the mechanism, right? Whether or not it's important to reagents, bonds breaking and forming. So while we aren't going to come up with rate laws, while we aren't going to calculate rate constants, please hear me again. We are not calculating much of anything. We are not calculating rate constants. However, rate constants were calculated to come up with the mechanisms that we're going to look at. So I am not teaching you how to program the computer, but I am teaching you how to use the program once it is made, right? That is sort of the analogy I like to use here. All of these first sections of chapter 6 are just reminding you of all of the important building blocks that you learned as you went through Gen Chem, that we are now building on top of. We are seeing the application of those building blocks in organic chemistry. So first order, second order, third order, that had to do with, right, how is the rate affected by the concentration of the starting material? If you only see A, that means, let's say if this was, our A plus B equals or yields C. If the rate law only has A in it, that means as long as B is present, the reaction will go forward. The rate is only affected by A, as opposed to, the second and third order ones where both A and B are important. This is really helpful information for figuring out how a reaction goes forward. Again, we're going to see these over and over again. This activation energy right here is helpful in understanding, right, what is the energy obstacle we have to get over, right? We have to have enough energy so that when our reactants collide, we can get over this hump before we make it to products. And that is where we see something called intermediates. Activation energy is affected by temperature. This is a Maxwell distribution. You maybe have seen this in general chemistry. You know that temperature is an average of the kinetic energy. So you have molecules that are lower energy and molecules that are higher energy, but then you have an average kinetic energy. And when you raise the temperature, right, what you're really doing is you're just moving this. So if your activation energy is here, right, when we raise the temperature, now more molecules have enough energy to get over that hump, get over that barrier. And that's why we heat up a lot of our reactions, right? So that we have more molecules that are energetic enough to react, right? It speeds up our reaction. And that can be very easy to visually represent when we think about different reactions, ones that are faster versus ones that are slower. If we think about it in terms of their activation energy, right? A smaller activation energy, more molecules are going to have enough energy to react. So you're going to get to products faster. I knew this picture was coming. Just there's that visual representation of why higher temperature can speed up your reaction. Okay. Steric considerations. Like I mentioned a moment ago, if we are dealing with A plus B, well, that means that A and B have to bump into each other, right, to react. But, think about your acid and base reactions. If your acid and your base don't bump into each other in the direction that is going to put the electrons from the base and the proton from the acid together, a reaction may not happen even if they have enough kinetic energy. So the steric considerations, the size and shape of the molecules, will also play a role. If you've got big, bulky molecules, they may not react as quickly because the number of successful interactions is going to be lower because there's just more surface area. Right? So we will bring up this idea of sterics throughout our time together. And then catalysts are interesting, and we'll see some discussions of catalysts as we talk through different reactions. But a catalyst can speed up a reaction. It doesn't change your starting materials and your products. What it does is it changes what happens here in the middle. It changes the order in which the bonds are breaking and forming to bring down that activation energy. You bring down the activation energy, more molecules have enough energy to interact, you're going to get to products faster. So it changes the mechanism. Just reading energy diagrams, we've been talking about this, but just a few things just to reiterate and point out before we go to part 2. Reactants are at the start, products are at the end. The difference between reactants and the maxima on the graph is your activation energy. The difference between reactants and products is your overall change in energy. So the rate of the reaction is discussed when we talk about kinetics, and that is driven by activation energy. The thermodynamics of a reaction, right? What do the products versus the starting material look like? That is more directly tied to the difference in energy between reactants and products. And sometimes kinetics will drive a reaction to a certain product. Sometimes thermodynamics will drive a reaction to a different product. We will see examples of that, particularly in organic 2. And here's an example, a very general example of that. A and B could react to form E and F or C and D, right? So 2 different outcomes. And what is going to be favored? Well, in this case, it's pretty easy. C and D are likely to be favored. There is a smaller activation energy, meaning they are going to form faster. So C and D form faster, right? Lower activation energy. They are also lower in energy than the products, right? So this is bigger. So they are also more thermodynamically favored. So in this case, C and D are kinetically and thermodynamically favored. That's not always the case. Sometimes you get graphs that cross like this. And in this case, right, E and F form faster, right, because you have that lower activation energy here, but C and D are more stable. So it's very interesting. There is a kinetic favored product and there's a thermodynamic favored product. What's cool about these relationships are it gives you control, right? There are ways to manipulate a reaction to get the kinetic product or to get the thermodynamic product. And so that's why we have to discuss these terms up top before we get into specific reactions like this. Other important pieces of an energy diagram that you need to be familiar with. You know your starting material and your product, front and or start and finish. But some reaction diagrams have multiple maxima and minima. All of the maxima are transition states. This is where the bonds are breaking and forming. This is just a symbol for a transition state. Those are always your highest energy. This is where bonds are breaking or forming. If we think about our very basic acid-base reaction, right? The transition state, and I'm going to draw it in brackets here, would be where the base is forming a bond to the proton and the proton bond is breaking from the acid. This is going to be the highest energy point, right? You cannot isolate transition states. Now, this is a very straightforward reaction when we do these acid-base transfers. There are no intermediates when you just have a reaction diagram that goes start to finish. But we are going to look at more complex reactions that have multiple steps, and then there are going to be intermediates. Intermediates are more stable than transition states, not usually as stable as starting material and products. So a lot of times you'll get like your cation and anion intermediates will be these kind of like local minima. And we are going to look at a specific example here, but this is a reaction that we'll cover in chapter 7. You notice that the CH3Br is becoming CH3Cl. And so that transition state is just as the CBr bond is forming, or I'm sorry, as the CBr bond is breaking and the CCl bond is forming, just like what I drew here with our acid-base reaction. A different but very similar reaction, the bromine breaks first and you have an intermediate and then the chlorine bond adds. We are going to learn in chapter 7 the difference between this one-step reaction and this two-step reaction. If that is breaking your brain right now, don't worry about it. We're going to get there. We are not going to worry about the Hammond postulate, so I am going to skip through that. And we will pick up in part 2 talking about nucleophiles and electrophiles and all of the different patterns of reaction mechanisms.